The first law of thermodynamics. In this session, we will explore the fundamental principles of the first law of thermodynamics. Our discussion will begin with an introduction to the law itself, followed by an analysis of pressure-volume diagrams and their relationship to work. We will then examine specific thermodynamic processes, including isothermal, isobaric, isovolumetric, and adiabatic changes. Finally, we will look at various energy transfer mechanisms that play a role in these thermal systems. The first law of thermodynamics is essentially a specific application of the law of conservation of energy. It focuses on processes where the only change occurs in the internal energy of a system, with energy being transferred across the boundary through heat and work. Mathematically, we express this as the change in internal energy equals the energy added to the system by heat plus the work done on the system. In this context, we use the symbol E int for internal energy to ensure there is no confusion with potential energy, which often uses the symbol U. This law reminds us that energy cannot be created or destroyed, only transformed from one form to another, or transferred between a system and its surroundings. Pressure-volume diagrams, or PV diagrams, are vital tools for visualizing thermodynamic processes. The work done on a gas during a quasi-static process is equal to the negative of the area under the curve on one of these diagrams. It is crucial to understand that work is path-dependent, meaning the amount of work depends on the specific sequence of states the gas passes through from start to finish. We can see three different examples here. In the first case, a gas undergoes constant pressure compression, followed by a constant volume process. In the second, it undergoes a constant volume change, followed by constant pressure compression. The third shows an arbitrary compression, where both pressure and volume change continuously. In each case, the shaded area representing work is different. Let us take a closer look at how the path affects work. In the first figure, the gas is compressed at a constant initial pressure before being heated at a constant final volume. The work is calculated as negative pressure times the change in volume. In the second figure, the pressure is increased at a constant initial volume first, and then the gas is compressed at a higher constant pressure. The work done in this second scenario is greater than the first because the piston must move against a larger force throughout the compression. The third figure illustrates a more complex path where pressure and volume change simultaneously. These examples prove that you cannot determine work simply by knowing the initial and final states. You must know the exact path taken. Internal energy represents the total energy stored within a system. The change in internal energy increases when work is done on the gas or when heat is transferred into the system. An important distinction to make is that while heat and work are both path-dependent, the total change in internal energy is a state variable. This means that as long as you start and end at the same points, the change in internal energy remains the same regardless of how you got there. In the illustration, we see a piston cylinder apparatus where work is being performed by pushing the piston down while heat is simultaneously entering the system, both contributing to a rise in the internal energy of the gas. We can apply the first law to special scenarios like isolated systems and cyclic processes. An isolated system does not interact with its surroundings, meaning no heat is exchanged and no work is done. Consequently, the change in internal energy for an isolated system is zero. A cyclic process is one that eventually returns to its original state, forming a closed loop on a PV diagram. Because internal energy is a state variable, the total change in internal energy over a full cycle must be zero. For these cycles, the energy added to the system by heat must be equal to the negative of the work done on the system, which corresponds to the area enclosed by the loop. An isothermal process occurs when the temperature of a system remains constant. For an ideal gas, internal energy depends only on temperature, so the change in internal energy during an isothermal process is zero. Applying the first law, this implies that the heat added to the system equals the negative of the work done on it. On a PV diagram, this process appears as a curve called an isotherm, which takes the shape of a hyperbola. The relationship is defined by the ideal gas law, stating that pressure times volume equals the number of moles times the gas constant times the constant temperature. To find the work done during an isothermal expansion or compression, we integrate the pressure over the change in volume. Using the ideal gas law, this results in a formula where work equals the number of moles times the gas constant times the temperature, multiplied by the natural logarithm of the ratio of the initial volume to the final volume. If the gas expands, meaning the final volume is larger than the initial volume, the work value will be negative, indicating work is done by the gas. Conversely, if the gas is compressed and the final volume is smaller, the work value is positive, meaning work is done on the gas by an external force. An isobaric process is one that takes place at a constant pressure. On a PV diagram, this is represented by a horizontal line. The work done on the gas in this case is straightforward to calculate. It is the negative of the constant pressure multiplied by the difference between the final and initial volumes. Usually, in an isobaric process, both the heat transfer and the work done are non-zero values. As the gas moves along this horizontal line from an initial volume to a final volume, it crosses different isotherms, indicating that the temperature of the gas is changing as it expands or contracts at constant pressure. An isovolumetric process, also known as an isochoric process, occurs at a constant volume. This appears as a vertical line on a PV diagram. Because there is no change in volume, the work done on or by the gas is zero. Referring back to the first law, this means the change in internal energy is exactly equal to the heat transferred into or out of the system. In this scenario, all the energy added to the system via heat stays within the gas as internal energy, typically resulting in an increase in pressure and temperature as the gas moves to a higher isotherm. An adiabatic process is defined by the fact that no energy enters or leaves the system as heat. This can be achieved by using heavy thermal insulation or by performing the process so quickly that there is no time for heat to exchange. In an adiabatic process, the change in internal energy is exactly equal to the work done on the system. If a gas is compressed adiabatically, the work done is positive, which leads to an increase in internal energy and a subsequent rise in the temperature of the gas. This is why a bicycle pump feels warm after rapid use. Let us test our understanding by identifying the paths shown in this diagram. The blue curves represent isotherms at different temperatures. Path A is a vertical line, which indicates an isovolumetric process where volume is constant. Path D is a horizontal line, representing an isobaric process at constant pressure. Path C follows one of the blue curves, making it an isothermal process. Finally, path B is steeper than the isotherms and is identified as an adiabatic process because no heat is exchanged. Notice how each path starts at the same state but leads to a different final temperature and pressure. Consider the example of boiling water. When 1 gram of water vaporizes at a constant atmospheric pressure, it undergoes an isobaric expansion. The volume increases significantly as the liquid turns to steam. The work done is calculated as negative pressure times the change in volume, resulting in negative 169 joules. The heat required for this phase change is found using the mass and the latent heat of vaporization, equaling 2,260 joules. By adding these together, we find the change in internal energy is 2.09 kilojoules. Interestingly, 93% of the energy goes into increasing the internal energy of the molecules, while only 7% is used to do work against the surrounding atmosphere. In summary, the first law of thermodynamics states that the change in internal energy equals heat plus work. Work is a path-dependent quantity and can be visualized as the area under a PV curve. Internal energy is a state variable, meaning its change is zero for any cyclic process or for an ideal gas undergoing an isothermal process. We have categorized 4 special processes: adiabatic, where there is no heat transfer; isovolumetric, where no work is done; isobaric, which occurs at constant pressure; and isothermal, which occurs at a constant temperature. To conclude, let us reflect on a few review questions. First, why does the work done on a gas depend on the path taken between two states? Remember that work is the area under the curve. Different paths cover different areas, representing different amounts of energy transfer. Second, in an isothermal expansion of an ideal gas, the temperature stays the same. Does this mean no heat is exchanged? Based on the first law, the answer is no. Since the gas is expanding and doing work, heat must enter the system to keep the internal energy and temperature constant. This ensures that the energy leaving as work is balanced by the energy entering as heat.